With today's supplemental lecture, and we're discussing another subtlety of the E2 reaction, and specifically looking at cyclohexene formation. So the E2 reaction requires the proton and the leaving group to be anti-periplanar. Now, in cyclohexane systems, this requires the hydrogen and leaving group to be trans-diaxial. So if we look at our equatorial groups for a moment, and we were to draw out our sigma star, the overlap between our sigma star and our carbon-hydrogen bond is not very good when they're in the equatorial position. If we compare to the diaxial arrangement, there's a reasonably good overlap between our sigma star and the adjacent carbon-hydrogen bond, which allows for an E2 reaction to occur efficiently. So our trans-diequatorial arrangement of our hydrogen and our bromine atom, when it undergoes a ring flip, will give the trans-diaxial conformation. This trans-diaxial conformation is the actual reactive conformation in an E2 reaction. Does that make sense to everyone? Does everyone remember this idea that in an E2 reaction, the proton and the leaving group must be anti-periplanar, so that way when your base abstracts your proton, you fill your sigma star and you form your new pi bond. You need to have this anti-periplanar arrangement. And for cyclohexane systems, they must be trans-diaxial. So both of these criteria must be met. So let's look and see. So if we have, for example, an axial chlorine, we have two hydrogens that are anti-periplanar. So we could potentially eliminate using hydrogen 1 or hydrogen 2. For our equatorial chlorine, there's no reaction from this conformation. However, if we undergo a ring flip, so first and foremost, before we move on from this, does everyone see very clearly how the overlap and the relative position of our hydrogen and chlorine atom in the diequatorial arrangement is not anti-periplanar? Does everyone see how they're not directly anti to one another? Okay. However, after a ring flip, and this is why these problems love to show up on exams, because they encapsulate the idea of ring flips, axial arrangements, equatorial arrangements. After a ring flip, so 1, 4, carbon 4 goes up, carbon 1 goes down. This chlorine ends up in the axial position. Because notice this chlorine is up. This compound looks like this. Chlorine is up. After a ring flip, we have a chlorine that is axial up, and now we have two anti-periplanar hydrogens. And so in the presence of a base, we can see a reaction to generate our elimination product. Key thing, it's these axial hydrogens that are reactive, because they're in the trans-diaxial arrangement relative to our leaving group. Does that make sense to everyone? Okay, so you can see why these examples are loved on exams, because they encapsulate drawing cyclohexane conformations and using them to understand selectivity in reactions. Okay. So the only way the leaving group and the CH bond can be anti-periplanar is if they're on opposite faces of the ring. So in other words, trans-diaxial. So you can end up in situations where suppose we have two hydrogens. So notice the hydrogen in blue and red. Which hydrogen can react? Which hydrogen can react? The one in red or the one in blue? Which one is anti-periplanar? Which one is transdiaxial? Only the one in blue. So only the transdiaxial hydrogen can react. This is important because as you notice, if we look at this product, this is the anti-Zaitsev product. It is generating the least substituted alkene. Does everyone see how this product formation is very unique and unusual? Because typically we want to form the most substituted alkene. But in this case, we're forming the least substituted alkene. And that has to do with the unique geometric requirement of the E2 reaction. So let's just do another example here. So depending on your relative arrangement of your substituents, now looking at this next example, can our red hydrogen now react? Can our red hydrogen now react? Is it anti-periplanar? So in this case, if there is a choice, if there are two transdiaxial hydrogen, the most substituted alkene is preferred. Okay, so geometric constraints being equal, the more substituted alkene is preferred. Has a lower activation energy, remember, because our transition state is alkene-like in character. So the more substituted the alkene you're generating, the lower in energy your transition state, the lower your activation energy, the faster your reaction. Okay, so I even said that right here. Okay, so let's look at some applications of this. So you may say, well, that's great. I just draw my cyclohexane conformation, I ring flip it, and I identify my transdiaxial hydrogens. So now, one important catch to all of this is a ring flip is required to generate the less stable transdiaxial conformation. And I'm just going to put in parentheses the usually less stable transdiaxial conformation. Now, because typically the transdiaxial conformation is higher in energy, the barrier to a ring flip directly influences the amount of transdiaxial conformation at equilibrium. And to figure out the amount of this less favored conformation at equilibrium, we have to look at the difference in energy between the axial and equatorial conformations, right? Because from our discussion, the equilibrium constant is based on the difference in relative energy of each of these conformations. So, for example, looking at the following system where we have an equatorial bromine and an equatorial methyl group, is this initial conformation reactive? Do we have transdiaxial hydrogens? Is this initial conformation that I've starred reactive? No. So it has to undergo a ring flip. So notice how this conformation is less stable because it has these nasty 1,3 diaxial interactions. So there's a little bit of an energetic barrier towards generating your reactive conformation. Once your reactive conformation is generated, then and only then do you have these transdiaxial hydrogens that can eliminate. Now, if we compare these two diastereomers, these two, well, it's a meso compound, but two compounds with slightly different orientations of our methyl group, we'll notice something a little bit interesting. When this second compound, which has an axial methyl, undergoes a ring flip, the diaxial conformation is more stable in this case. Does everyone see why the diaxial conformation is more stable for our second compound? Because our methyl group is now equatorial. Okay, so depending on the relative energy of your two conformations, you may have to climb up a relatively large or small activation barrier. Now a consequence of this is this top reaction has a larger barrier, and as a result, it's a slower reaction. This bottom reaction is much faster. So when you hear the words, which reaction is faster, I want you to consider, what is the barrier to my ring flip? Is it large or small? And if the barrier is smaller to undergo a ring flip to generate your diaxial conformation, then that E2 reaction will occur faster. Does that make sense? Is everyone comfortable with this idea? Okay, so in general, the greater the amount of the diaxial conformer and the lower the relative energy of the diaxial conformer, the faster the rate of E2 reaction. So again, these make great test questions. Now, let's take a look at the following reaction. Let's try to predict the product of the following reaction, draw the chair conformation that reacts, and draw a mechanism. Okay, so first and foremost, both of these substituents are up. Can everyone clearly see that both of our substituents are up? The wedge, they're up. So now what I'm going to do is I'm going to make a quick little model. I'm going to make a quick little model for this compound. And again, this is another case where your model kit will save you a lot of grief on the exam. So make sure you have your model kit ready to go. Okay, and now we're going to populate our cyclohexane ring with hydrogens. So let's put together a model of this compound. Give me about 1 minute, just putting it together and checking that it looks good in the camera. Okay, so here is the model. Here's the model of our cyclohexane system. So we notice that both our hydrogen and our methyl are pointing towards us. Both our bromine and our methyl are pointing towards us. Now let's look at this structure from a side-on perspective, and let's try to see. So currently, do we have a trans-diaxial arrangement? Do we have a trans-diaxial arrangement between our bromine and our hydrogen? Yes, so we have multiple choices to choose from. We can either pick the hydrogen on the left or the hydrogen on the right. So we have two choices. Let me just flip these really quickly. The camera inverts my models, so let me just showcase that. Okay, So in this case, when we look at our lowest energy conformation, we clearly see that we have two transdiaxial hydrogens. So we have the following hydrogens. Allow me to draw out the chair conformation that we've just drawn. So first, here's our lowest energy chair conformation. I'm only drawing the relevant hydrogens. If we wanted to ring flip this compound, we get the following arrangement. The only problem is, can the bromine react in the equatorial position? Can the bromine react in the equatorial position? No. So if we look at our post-ring flip structure, not only is it higher energy, but it's less reactive. Okay, so the conformation on the left is the most reactive. It's the only one that can react. We have a choice of two hydrogens. So A or B. Which hydrogen is more reactive? Which hydrogen is more reactive? Which hydrogen will give us the most substituted alkene? A or B? A. So our base is going to react. So in this case, we have ethoxide. It will abstract a hydrogen. The hydrogen will eliminate and will form our alkene. So let's draw out our alkene. It's the most substituted alkene. And this is only possible because our bromine and our hydrogen are transdiaxial. Does that make sense to everyone?
Excuse me, Professor.
Yes.
Can you explain what transdiaxial is? How did you pick the hydrogen to be transdiaxial?
Okay. So notice in dash wedge notation here, this bromine is up and this hydrogen is down. The bromine is wedge and the hydrogen is dash. They have opposite stereochemistry, so they're trans. They're on opposite sides of the ring. So just to showcase that. So if we look at our bromine and our hydrogen, or on either side, do you notice how they're on opposite sides of the ring? One of them is pointing up, the other is pointing down.
Yeah.
And do you notice how they're both in the axial position? Yep.
Yes.
So we call them trans since they're on opposite sides, and then diaxial since they're both in the axial position.
Oh, okay.
Does that make sense?
Yes, got it. Thank you.
If you're looking at dash wedge, if the bromine and the hydrogen have opposite stereochemistries on adjacent hydrogens, then they're trans to each other. You have to draw out the chair conformation just to verify that the diaxial conformation is in fact accessible. Does that make sense?
Yes.
In terms of which proton we picked, we wanted to generate the most substituted alkene in parentheses from a transdiaxial transition state, or from a transdiaxial conformation. Let's use that word. So first you check for the reactive conformation that the leaving group and the hydrogen are transdiaxial, and then you think, which hydrogen gives me the most substituted alkene? Does that make sense?
Yes, it does. Thank you.
Perfect. So let's look at another example now. Let's look at another example. Now you may say, you didn't really change much, right? Well, I'd like you to take about 3 to 5 minutes and look at the following example and try to predict the product from this reaction. And just as a hint, you get an almost entirely different product. So don't be shy to type your proposed answer in the chat. You can type the name of the compound, or you can try drawing this compound using the annotate feature. And we'll discuss in about 3 to 4 minutes. And don't be shy to make a model of this compound. It may look really subtle, but there's a massive difference in how this compound reacts. And to give everyone a hint and to help everyone facilitate their discussions, there are 2 potential products that we could form. A or B. And I'd like you to message me in the chat when you've come up with a reasonable solution, whether product A or B is formed. But really make sure to think this question through. Don't rush to conclusions and take it step by step. And we'll discuss in about 3 minutes. And don't be shy to ask any questions in the chat or verbally. And let's get a few more responses in the chat and we'll discuss in about 2 minutes. Any questions? Would anyone like to propose a solution using the annotate tool? If not, we'll discuss in about 1 minute. So let's discuss this problem. So first and foremost, the bromine is up, the methyl is down. So starting off, I'm going to draw one conformation. It may not necessarily be the lowest energy. So our bromine is up. So I'm going to draw it axial up. And the methyl is down. And instead of being equatorial, it's axial down. Okay, so let's put our methyl axial down. And now let's draw our hydrogens. Let's draw the hydrogens that are critical to this whole process. Okay, we've drawn our hydrogens. Let's look at our other accessible conformation. Oh, whoops, I made a mistake here. This is a common mistake. Make sure that carbon 1 goes down, carbon 4 goes up. Carbon 1, the bromine is up. So now instead of being axial up, it's equatorial up. We'll draw both of our hydrogens. Now, my question to all of you is, which conformation is reactive? Conformation 1 or 2? Which conformation is the reactive conformation? Conformation 1, exactly right, because it has this trans-diaxial arrangement. Our bromine is axial. So conformation 1 is reactive. However, if we think about our relative energy, which conformation is the lowest energy conformation? Which conformation, whoops, let me put the methyl in here. Which conformation is the lowest energy conformation? 1 or 2? Which conformation 2, exactly right. So conformation 2 is lower in energy. Why? Well, this methyl, unfortunately, in conformation 1, experiences a fair amount of 1,3 diaxial interactions, which unfortunately costs us a fair amount of an energetic penalty. Okay, so now that we've done our relative assessment of each of the conformations, let's try to identify which hydrogens can react. So hydrogen A or hydrogen B. Which hydrogen can react? Which hydrogen can react? Hydrogen A or hydrogen B? Which hydrogen is trans-diaxial to the bromine? Hydrogen B, exactly right. So our ethoxide is going to go in, it's going to pull off our hydrogen, and we'll eliminate our bromine to exclusively yield product B. So this is the only product. So notice how a subtle change in stereochemistry results in a substantial change in the regioselectivity of our E2 reaction. Does that make sense to everyone? Okay, so just to show this with the model kit, our bromine is axial. The hydrogen attached to the methyl is equatorial. We only have a diaxial hydrogen on our adjacent methylene group. So we can only have reaction on the left-hand side. Does that make sense to everyone? Okay, perfect. So let's keep continuing on. So let's look at the following example. Let's try to answer the question, which of the following molecules have a faster rate of E2 reaction? So you have to draw some chair conformations to justify your answer. And I'd like you to identify the products from each of these substrates. Let's take about 4 to 5 minutes to work through this problem, and then we'll come together as a group to discuss. And don't be shy to break out the annotate tool to draw out your proposed products. Oh, don't be shy to continue on with the drawing. It looked good so far, but make sure to consider the lowest energy conformation. So you have to draw both of them. Oh, I think the chlorine, is the chlorine in the correct spot? The relative arrangement of the methyl and the isopropyl group is good. Would someone else like to try drawing some conformations for the structure on the right? Well, there are two structures, and it would be nice to have input for both the structures. But so far, let's keep going with the structure on the left. It's looking good so far. Ah, I see. Okay, that makes more sense. Okay, perfect. Now try to draw out and identify your reactive hydrogens for elimination, and then draw the product. Is the leftmost hydrogen that you circled adjacent in an adjacent atom? The rightmost hydrogen looks good, but the one that's on the left, yes, you can choose to make isopropyl number 1 in terms of carbon numbering if it makes things easier. So the structure on the left looks good. Just try to carefully identify your trans-diaxial hydrogens, the hydrogens on an adjacent carbon that is also in the axial position that's trans to our leaving group. And there are 2 of them for the structure on the left. Yep, and yep, exactly. And then determine which one's more reactive. Which one would give you the more substituted alkene? The more substituted alkene? Yep, exactly right. And now you just have to draw the product. For the structure all the way on the right, it's looking good, but now try to draw the most reactive conformation. It looks good. Just get rid of the wedge on the isopropyl because the alkene is flat. Otherwise, it's perfect. No, the dash is fine, but it's just the wedge. And for the structure on the right, could you draw and identify the transdiaxial hydrogen? Everyone from the class is chipping in. We've almost completely solved this problem. All we need to do is identify our transdiaxial hydrogens for the structure on the right, and we're home free. Well, what I've seen so far looks very good. And let's just clear this. So I'll provide the instructor solution now. So first and foremost, the isopropyl is up, the chlorine's up, the methyl is down. Okay, so let's draw one of our conformations. So I'm gonna designate our isopropyl as equatorial. So I'm gonna put it at carbon 2, just because the bulky isopropyl group will almost never want to be axial. It's like a T-butyl group. It's a bike lock for conformations. The chlorine is up, so it'll be axial. And the methyl is down, so in this case, the methyl will be equatorial. Okay. Okay. Now we can show the ring flip. We can certainly do that, but we can clearly see what the reactive conformation is. But let's draw the ring flip just to show. Now, would we ever have an isopropyl group in the axial position? Are we ever going to see an axial isopropyl group? Are we ever going to see an axial isopropyl group in most cases? No. So this conformation is lower energy, and it's the reactive conformation, Okay, now we have to identify our transdiaxial hydrogens. So let's circle them here and here. Now, which hydrogen, A or B, would give us the most stable alkene? Which hydrogen, A or B, would give us the most stable alkene? B. Yep, exactly. So our base, so I'm just going to write our base as B. We'll abstract our proton, we kick out our leaving group, and we generate the following product. Here we go. Perfect. Now let's look at our structure on the right. Let's look at our structure on the right, and let's draw the chair conformation for that structure. So first and foremost, we have up, down, down. Again, I'm going to arbitrarily designate the isopropyl group in the equatorial position. The chlorine is equatorial down, and our methyl stays the same, it's equatorial. So let's now draw the ring flip. Let's now draw the ring flipped conformation. Okay, so unfortunately for us, which conformation is the reactive conformation? The conformation on the left or the right? Which conformation is the reactive conformation? The one on the right. Exactly, correct. However, the conformation on the right is higher in energy. And it's the reactive conformation. What this means is that this reaction is going to be very, very slow because we have to climb this absolutely massive energetic barrier to undergo a ring flip. Further, just to make things worse, how many trans-diaxial hydrogens do we have? How many trans-diaxial hydrogens do we have? Do we have a choice? We only have one choice here. This is the only trans-diaxial hydrogen. So upon elimination, which will be very slow, you will generate the following product. So the thing I want you to take away from this is that if you have a conformation, if your reactive conformation requires you to place bulky substituents in the axial position, your reaction is going to be very, very slow. Further, your product regioselectivity for an E2 reaction is dictated by having a trans-diaxial arrangement of your hydrogen and your leaving group. Does that make sense to everyone? Does this make sense so far? Now, here's the catch. I'm going to put a star next to this question because in reality, if you actually try to run this reaction, you may get a mixture of products. And that's because there's another reaction pathway that we are going to discuss now. But before we discuss the next major reaction pathway, we're going to discuss a bit of a side note that is important for 113. It's called the E1CB reaction. So it's a stepwise reaction where an acidic alpha proton, well, here's where things get a little bit of a matter of semantics. So depending on how you number it, you can call this a beta proton. It's deprotonated by the base to yield a stabilized anion. The reason I was about to replace it with alpha is in many cases, you will have an alpha proton in a leaving group and the alpha proton will be removed and then you kick out your leaving group. This is very common in chem in the next organic class. So depending on your numbering convention, essentially the proton is removed, you generate a stabilized anion, and then you have elimination of the leaving group to yield the alkene. Now, so in step one, you have deprotonation. So you generate a stabilized anion. Then in step two, which is rate limiting, in the second step of the E1CB, which is rate limiting, in the second step, your lone pair is kicked down and your leaving group is eliminated. That in turn generates the following product. That in turn generates the following product. So the second step in the E1CB reaction is rate limiting. And E1CB reactions are accelerated if the leaving group is good and the beta proton is acidic. So you're going to need your pKa table. So let's look at an energy diagram for an E1CB reaction. So first and foremost, you have step 1, which is deprotonation. So in step 1, your base is pulling off a proton. And then you're generating an anion intermediate. In the second step, we are eliminating our leaving group. So in our transition state, we have our anion, and we're in the process of forming our alkene and kicking out our leaving group. So we have an alkene-like transition state. I'd like you to think very similarly to the idea of an E2-like transition state. Except, and this is a critical distinction, it doesn't depend on the base anymore for step 2. Okay. So in transition state 1, we have deprotonation. Transition state 2, we're forming our pi bond with the loss of our leaving group. A key signpost for an E1CB reaction, 1 is strong base, and 2, electron withdrawing groups, such as, for example, CF3, which are commonly abbreviated as EWG if you're just describing a generic electron withdrawing group. Does this make sense so far to everyone? The E1CB reaction is stepwise. First you deprotonate, then you eliminate. If you see strong base and electron withdrawing groups, I want you to think E1CB. You'll see these a lot in 113. Okay, so here are some examples of E1CB reactions. So this is a classic step in what's known as the aldol condensation. So step 1, we have deprotonation. Step 2, we eliminate. Does everyone see our clear electron withdrawing group? Does everyone see our clear electron withdrawing group, our ketone functionality? That's a key signpost. Another example of an E1CB reaction is elimination of alkenyl halides to generate alkynes. In this case, the reason why this reaction works is that the pKa of this vinylic proton, what's the pKa of a vinylic proton around, roughly? What's the pKa value about? Ballpark. 20, 30, 35 of an alkene, yes. 25 is an alkyne, roughly. So the pKa of this vinylic proton is somewhere around, alkanes are around 50, yeah. So the pKa is somewhere around 33. Well, for our amine, the pKa is somewhere around 35 to 36. Just ballpark numbers. So first we have deprotonation to generate a relatively stable anion, because remember, sp2 anions are relatively stabilized by orbital effects. And then you generate your alkyne after elimination. So let's just do a quick little prediction. So if we are asked to predict the product from the following reaction, first things first, I see immediately I have an electron withdrawing group. So this tells me we have a clear signpost for an E1CB reaction. So first we have reversible generation of our anion. And the beautiful thing about E1CB reactions is your anion generation doesn't have to be quantitative. Because after elimination, it almost slams the door shut on the reverse process because it's very hard to regenerate your carbon leaving group bond. So this is a nice way of generating these conjugated esters, which are very reactive for addition reactions. Is everyone comfortable with the idea of the E1CB reaction? Okay. You won't see it a ton, but it is important to keep in mind it's stepwise, so it behaves differently than a normal E2. Okay, so I'd just like you to take a moment and looking at the following example that almost looks like a precursor to a tear gas agent or a lacrimator of sorts. I'd like you to predict the products from the following reaction and draw a mechanism. So if someone would like to break out the annotate tool and try to predict the products from this reaction, we'll discuss in about 2 minutes. This is a nice fast problem. Yep, we've clearly identified an electron withdrawing group. And now let's show the first step. Remember, the E1CB is stepwise. Yes. And yes, there's only one leaving group that will actually leave in this reaction. And the way you figure out which site is deprotonated is just by comparing the pKa's. And I'll give you a hint. If you think about the pKa of an alpha proton to an ester versus the pKa of an alpha proton to an ether, which proton's more acidic? Yep, exactly. So I'm seeing a lot of reasonable responses in the chat. So I'm just going to clear and we'll discuss this together. So if we compare the pKa's, this proton adjacent to our ester is the most acidic. So triethylamine, which is our base, is going to pull off a proton and we're going to generate a nice stabilized anion. Also stabilized by the fact we have an electron withdrawing bromine group. Next, our lone pair kicks down and we eliminate our leaving group to generate this, whoops, getting ahead of myself there. to generate this vinyl bromide. Here we go. So here's our final product, and we've even drawn a mechanism for this reaction. Any questions on this example? Okay, so let's keep going now. And let's look at another type of elimination reaction called the E1 reaction. So the E1 reaction is unimolecular, and the rate only depends on the concentration of substrate. Think very similar to SN1. Now the similarities don't just stop there. The rate of reaction increases with substitution, and this is where you begin to realize that the SN1 reaction, although it has some merits in some preparations, it's not commonly used for synthetic preparations because the E1 reaction competes with the SN1 reaction. They follow similar mechanisms and pathways and intermediates. So this should already be a red flag. So when you think E1, just like SN1s go through a carbocation-like intermediate, E1s also proceed through a carbocation intermediate. So in the E1 mechanism, first things first, just like the SN1, the leaving group leaves to form a carbocation. This step is rate limiting. This is exactly like the SN1 reaction, right? However, in the E1 mechanism, a proton is removed by the base to give an alkene. Now, just as a refresher, when we think about a proton adjacent to a carbocation, what's the pK of that proton, roughly? If we had to take a guess, is that proton going to be acidic or not very acidic in general? If it's adjacent to a carbocation, which I like to think is like a super electron withdrawing group, what's the pK of a proton next to a pretty strong electron withdrawing group? What's the pK going to be around? It's going to be quite acidic. These have a pK of around -1 to -3. Super acidic. Carbocations don't like to exist in solution for very long. So when I say base, really anything can do. And the base is commonly the solvent. Does this make sense to everyone so far? So when we say base, you're not looking for like a specific anion. In fact, many E1 reactions are run under acidic conditions. But because the proton adjacent to a carbocation is so activated, even weak bases will do the trick. Even water can function as a base in this case. Does that point make sense to everyone? Okay. Now, so the rate determining step is loss of a leaving group. The rate is proportional to carbocation stability. That's why we see the trend of tertiary, secondary, much greater than primary. And it follows the same pathway as the SN1 reaction. Now, as always, let's look at a reaction coordinate. I mean, we can't have a discussion without looking at the reaction coordinate. So the first step is identical to the SN1 reaction. This is identical to the SN1 reaction. It's the first step is loss of leaving group. It's the rate limiting step, losing our leaving group to make a carbocation intermediate. In the second step, we have elimination. If I were to draw, just overlaid on this chart, if I were to draw, so if red is looking at your typical SN1, this would be our SN1 pathway, and our second step would be addition. So to say that the E1 and SN1 are related, it's more, they follow the same initial rate limiting step and the second fast step of either elimination or addition compete with each other. So SN1 and E1 reactions are competing. And often you observe a mixture of products because your selectivity determining step and your rate limiting step are before you have differentiation between your SN1 and E1, right? You make the same intermediate in both of these pathways, but the fast step is what differentiates your SN1 and E1. So just to reiterate that once again, step 1 is rate determining. So it's loss of your leaving group is rate determining. The elimination step is fast. Okay, so let's look at some substrate effects. The reaction rate increases with substitution, and this is a unique trait of the E1 reaction. Carbocation stability, so primary, secondary, tertiary, and allylic / benzylic carbons. Remember, allylic and benzylic carbocations are especially stable. So if you're looking at elimination reactions and you see an allylic or benzylic position, I want you to think SN1E1, as those are far more common than SN2. Now, just like SN1, polar protic solvents stabilize the carbocation-like transition state, resulting in a faster rate of reaction. Further, the better the leaving group, the faster the rate of reaction, as the Gibbs energy of activation for the rate limiting step depends on the leaving group. Okay, perfect. So here's our coordinate once again. Remember, you should be familiar drawing out reaction coordinates and showing how changes in substrate and reaction conditions affect your reaction coordinate. Okay. So leaving groups are based on pKa values. Essentially the weaker the base, the better the leaving group, with some exceptions. Essentially, good leaving groups are large atoms or atoms that or molecules that can readily stabilize a negative charge, which are all the features of very, very weak bases. Does that make sense? Perfect. Okay, so the E1 is very similar to the SN1 in terms of character. So you often see the E1 and SN1 reactions competing. And in fact, if we look at the SN1 versus the E1 reaction, the SN1 and E1 reaction proceed through the same intermediate, where step 1, which is loss of the leaving group, step 1 is rate limiting. Once you have your carbocation intermediate, that intermediate can react through multiple different pathways, either substitution or elimination. And unfortunately, step 2 is not rate limiting, which results in low selectivity between E1 versus SN1 pathways. So you'll inevitably get a mixture when you run these reactions. So, but there's a trick. SN1 products are favored if a strong nucleophile is present at low temperatures. So just put a star next to temperature, Because remember, elimination versus substitution is influenced by temperature. Why? Because elimination reactions are favored by entropy, while substitution reactions are favored by enthalpy generally. So if you start increasing the temperature, you're going to start to see a lot of elimination. E1 products are observed if you have no nucleophile or a very weak nucleophile, and the reaction is run at high temperatures. But either way, mixtures are almost inevitable. And that doesn't even begin to entertain the fact that this carbocation can shift and do all sorts of weird rearrangements. So in terms of stereoselectivity, SN2 and E2 reactions are far more useful, unless you have neighboring group participation. So let's look at the regiochemical outcome of the E1 reaction. So E1 reactions prefer to generate the most stable, most substituted alkene. Makes sense. However, mixtures of regioisomers and stereoisomers are observed. Did we see that in one of our labs? Did we see this mixture phenomena? What lab did we observe this effect? Did we run an E1 reaction before? What lab is almost this exact substrate? The 2-butanol lab, exactly right. When we collected the mixture of products, and we got not only a mixture of regioisomers, but also a mixture of stereoisomers. So just an absolute mess. So these are E1 products, and this is our SN1 product. So you really do get a mixture, but in general, the E isomer is preferred and the most substituted alkene is preferred, but mixtures of products are unavoidable. So if we compare an E1 and E2, and sometimes, remember how I said, sometimes when you try to run an E2 reaction, you end up getting a little bit unlucky? Well, strong base is needed for an E2, but not for an E1. So that's one distinction, the base strength. The E2 is stereospecific. It requires the trans-diaxial arrangement. But the E1 reaction is not stereospecific. So, quote unquote, trying to force, so like forcing E2 reactions at high temperatures can give E1 products if the E2 reaction is not geometrically allowed. So, what do I mean by that? So under E2 conditions, if you use a strong base and concentrated base, you observe elimination from the trans-diaxial conformation. If you're running this reaction under E1 conditions with dilute base, you instead see elimination with no stereo selectivity or stereo specificity. This is why for an E1 reaction gives a mixture of products, because the carbocation can react with, and you can eliminate any of your adjacent hydrogens, regardless of whether they're transdiaxial or equatorial. Does this distinction between E1 and E2 make sense? E2 reactions are stereospecific. They require a unique, specific conformation for a reaction to occur. E1 reactions are not as selective, and they give mixtures of products. Does that make sense to everyone? So sometimes if a student gets really frustrated and they see that their E2 reaction in the lab isn't working, they think, let me just turn the temperature up really, really high, and maybe I'll get this species to eliminate. Well, that's great, but if an E2 reaction is not geometrically allowed, you're just going to see E1 products. Okay, so let's keep going now. Hopefully. So let's try to draw a mechanism for the following E1 reactions and predict the products. So first things first, step 1, our leaving group leaves and we make a carbocation. Now, thankfully, I'm not being too mean in this first problem and having us entertain the idea of carbocation rearrangements. So now we have multiple protons to choose from. So let's just pick one of these protons, and our base in this case is ethanol. So it's going to pull off a proton. We're going to eliminate our proton, and we're going to generate the following alkene, the most substituted alkene. Of course, we're going to see a mixture of products. That's inevitable. And these two products will be our major products. Alternatively, in terms of our minor products, if we eliminate to generate our least substituted alkene, we generate the following product as a minor product. And of course, our carbocation could be intercepted with our nucleophile, so we'd also generate our SN1 product as a minor product. Does that make sense to everyone? Any questions so far? Okay, let's keep going now, and let's take a look at this next reaction. So if we're entertaining the idea of an E2 reaction, yes, SN1 is fastest at a tertiary carbon. SN2, which is what you're likely thinking of, which occurs through a concerted mechanism rather than stepwise. SN2 reactions are slowest as substitution increases. So in general, you see SN1 at tertiary carbons and SN2 at primary carbons. So the carbocation intermediate is the key intermediate for the SN1 reaction. And in fact, the SN1 reaction is fastest for tertiary carbons. Did that clarify your question? Perfect. Okay, so supposing this is an E1 reaction, let's draw our first step, which is loss of our leaving group to make a carbocation. Now this is where things can get a little bit tricky. My question to all of you is, can I make a more stable carbocation? Can I make a more stable carbocation? Yes, and what process would give us a more stable carbocation? What do we call that process? Hydride shift, exactly right. So after a hydride shift, there are some cases where you have alkyl shifts. So you really don't want to go through a carbocationic intermediate unless you can impart some control. Now from this intermediate, we have a few pathways. So let's draw down here like our typical SN1 pathway, where your methanol attacks, you generate the methoxide or methanol adduct, and then another equivalent of methanol pulls off that last proton, and we get the following product, which if you're not expecting it, you'd wonder what is going on. The other option is to eliminate. Remember, hydrogens adjacent to a carbocation are relatively acidic. So this would be a major product. And then as a minor product, we generate the following alkene as a minor product. Does this make sense to everyone so far? Everyone comfortable with this idea? Okay, so let's keep going now. So here's a summary table. Now, I'm not going to go through and read every single aspect of this table, but I want you to have this as it essentially summarizes every aspect of the SN1, SN2, E1, and E2 reactions. So key things, key highlights. So SN2, the key features that I want you to keep in mind, they deal with a strong nucleophile with minimal steric bulk. They prefer primary and secondary substrates and aprotic solvents. The mechanism is concerted with inversion of our stereocenter. Okay, let's look at the SN1 reaction. The SN1 reaction is based on carbocation stability. The nucleophile doesn't matter, but a strong nucleophile and a weak base certainly helps. They like protic solvents. The mechanism is stepwise and a racemate is observed. Okay, let's summarize the E2 reaction just as highlights. The E2 reaction is based on alkene stability with tertiary leaving groups reacting the fastest. They want a weak non-nucleophile and a strong base is absolutely required. E2 reactions prefer aprotic solvents. They're stereospecific and require an anti-periplanar arrangement. Finally, our E1 reaction, again, is based on carbocation stability. So they prefer substituted allylic and benzylic substrates. They want a weak nucleophile and a weak base. And they prefer polar protic solvents with heat added. These are not stereospecific reactions. Do these summary highlights make sense? So this is just a nice little table you can look back on, and it summarizes everything that you'll see for these reactions. So it's just something to keep as a reference if you want to quickly review your notes. Any questions on this summary? Yes.
Professor, can you quickly go back to page A5?
Sure.
All right, thank you. Got it.
Yep, no problem at all. Any questions from this summary? So if you prefer processing your data in a little bit of a different manner, so in tabular format, here's a summary of SN1, SN2, E1, and E2 reactions. So I think of it a little bit like a flow chart where I look at my substrate. So if I see primary substrates, we're immediately in the domain of SN2 and E2. Now, if you have a secondary substrate, then it's a bit of a guessing game, and then you have to go down and look and see your nucleophile, whether it's strong or weak. Now, if you have a strong nucleophile, you're primarily dealing with an SN2 reaction. If your base is weak, that's another checkbox for the SN2 reaction. And you'll just go through this table and start looking at your substrate, then you look at your nucleophile, then the base, then the solvent. And depending on the differentiating factor in your reaction conditions, the conditions will either favor SN2, E2, E1, or SN1 reactions. So this is just a nice little summary to help you differentiate these different reaction pathways. Does that make sense to everyone so far? Is everyone comfortable reading this table if they want to use it as a reference? Of course, it's perfectly optional, but it summarizes our discussion into as small of a amount of text as possible. If you want a flow chart, this is how I like to think through my reactions. I ask myself, is my substrate primary, secondary, tertiary, allylic, or benzylic? If it's primary, I then ask myself, is the nucleophile strong or weak? If it's strong, I'm in the SN2 domain. If it's weak, then I ask myself, is the base strong or weak? If it's strong, we're in the E2 domain. If it's secondary or allylic, I ask myself, is the nucleophile strong or weak? If it's strong, we're in the SN2. Okay? If the nucleophile is weak, then we ask ourselves, is the base strong or weak? If the base is strong, we're in the E2 domain once again. If the base is weak, then I ask myself, is the nucleophile strong or weak? If it's strong, SN1. If it's weak, an E1, but we often see a mixture. So that's another way of thinking through whichever table you prefer to use as a summary. Note, these tables only give you a tool to predict the mechanistic pathway that a reaction will go through. This table does not provide you any information on the intricacies of an SN1, SN2, E1, or E2 reaction. So you need to remember all of the geometric constraints and all of the mechanistic details of these reactions for the exam as well. Does that make sense to everyone? Do these tables make sense? Okay, so just as another reference, here's a table of common nucleophiles and bases sorted by strength. Here's a table of your common strong bases, and here's a table of your common polar protic solvents. Now, just to show the application of this table, let's try to predict the major and minor products from the following reaction. So looking at the following reaction, we have sodium hydroxide. And looking at this position, is it primary, secondary, or tertiary? Is this carbon primary, secondary, or tertiary? So it's secondary, okay. Now, looking at our base, so we have a secondary substrate. Is our base going to be strong or weak? Is our base strong or weak? Our base is strong. What about our nucleophile? Is our nucleophile strong or weak? Is hydroxide a strong or weak nucleophile? Relatively strong. Okay, so a strong base on a secondary substrate, that looks a lot like E2 to me. A strong nucleophile also says SN1. Oh, sorry, SN2. So strong nucleophile, SN2, strong base, E2. So then we're going to see a mixture of products. So let's first entertain the SN2 pathway. Let's first entertain the SN2 pathway. Okay, so we're going to do a slight rotation. So we're going to rotate this carbon-carbon bond. to yield the following arrangement. And now hydroxide is going to attack, and it's going to invert our stereocenter to give us the following product. Which is equivalent after a reverse rotation to the following structure. Okay, so we've entertained the SN2 pathway. Remember, the SN2 pathway occurs with inversion. Now let's entertain the E2 pathway. So to help us visualize both of these reactions, let's take a moment and let's make a model kit. Let's make a model.
Professor, I have a question.
Yes.
For the SN2, like, how do you know you've rotated it enough for the inversion?
So the reason why I rotated in this case is so that way I can just replace my leaving group with a dash with my nucleophile with a wedge. It's easier to show inversion when you have your leaving group written in dash wedge notation. Since all you do is swap out your leaving group and change the stereochemistry of your leaving group to the opposite configuration for your nucleophile.
Okay, got it. Makes sense.
Yeah.
Thank you.
Mm-hmm. So let's make a model and let's just showcase the key bonds. So the cyclohexane ring is it's just an add-on. It doesn't actually play a huge role in this reaction pathway. So let's focus on our key bonds in that side chain. So I'm going to put together a model. And the reason why I'm putting it together a model is because the SN2 and E2 reactions are stereospecific. So we have to be very careful with how we describe and how we portray the stereochemistry of our products. Because the E2 and SN2 reactions give products with defined stereochemistry. So let's put together a model of this structure and then we'll discuss momentarily. One moment, almost complete with the putting together the model. Okay, so let's get the view just perfect. Okay, here we go. So we have our bromine, We have our chain. We have both of our methyls. Are both of our methyls pointing towards us right now? Are both of our methyls pointing towards us? Yes. Okay, so what we did very simply is we rotated our molecule. So now does everyone notice how our bromine, is it pointing towards or away from us? Is the bromine, it's pointing away from us. So if we attack it with a nucleophile, it will come from the opposite side, which is the front face. And now when our hydroxide is installed, is our hydroxide pointing towards or away from us? Is this red oxygen? It's pointing towards us, right? So just to show the inversion, when we kick out our leaving group, our nucleophile is added from the opposite face. So now our center has the opposite configuration. Now, just to show this rotation, if I rotate my structure back so that the hydrogen is in the plane of the page, is our alcohol pointing towards or away from us? Is this OH pointing towards or away from us? Away. Yeah, the alcohol is pointing away. And is the methyl pointing towards us? Is the methyl pointing towards us? Yes. Okay. So I'm not just making this model kit for fun. There's another purpose to making this model kit. It's going to be invaluable. It'll be priceless in helping us identify and draw out the products from this E2 reaction. So, oops. Let me get this just right. Let's return to our same starting point. Okay, here we go. So we're back to our same straight chain. We rotated it. So our methyls are in the plane of the page. Now what we're going to do is we're going to look down. We're going to look down our carbon-carbon bond, and we're going to draw a Newman projection. So in the front, what do we have on the right-hand side? What do we have on the right-hand side? Bromine. Okay. What do we have on the left-hand side? Methyl, and pointing down is the hydrogen. In the back, what do we have on the right-hand side? What's this giant group on the right-hand side? On the right, not a benzene, but a cyclohexane ring. Okay, now still looking down our bond, what is pointing up in the back? What is pointing up in the back? Hydrogen, and then to the right, we have our methyl group. Wonderful. Okay, now we're gonna do a rotation. We're gonna rotate in front, so our bromine and hydrogen are anti to each other. So that in turn gives us the following Newman projection arrangement. So just to show that with our model kit, here we go. So we arrange it. So our bromine and hydrogen, let me set it up so that way we can see it exactly as drawn. So our bromine and hydrogen are anti to each other. Now, after elimination, what groups will we have on the right? What groups will we have on the right after After our elimination, what groups will we have on the right? What's on the right in this picture? So what's on the right of our alkene? So what groups do we see on the right? We have a methyl, yeah. We have the methyl in front. Yep, that's for sure. Okay, and what else? What else is on the right? The cyclohexane ring. One moment, let me just check our structure really quickly. Oh, I apologize. Again, the camera flipped the model around. One moment. Yep, so we have our methyl group and our cyclohexane ring on the right. And then on the left, we have our hydrogen and the methyl group. So we generate one product with stereo specificity. So again, just to showcase what we did, first and foremost, we start from the conformation exactly as drawn. We then look down our carbon-carbon bond and we rotate our molecule so the hydrogen and our bromine are trans to each other. Anti-periplanar is another way of putting it. We then look at all of the substituents on the right, which is our methyl and our cyclohexane. All of our substituents on the left are our hydrogen and our methyl group. After elimination, we draw our alkene based on this conformation. So these are the two products that we'd observe from this reaction. Does that make sense to everyone? Does this line of analysis make sense? So anytime you see SN2 or E2, you would need to make a model. That's my recommendation. Hydrochloric acid, so that's not a very strong nucleophile, so you'd probably see like SN1 or E1 products. Sodium chloride, that would also make mainly SN1 because the nucleophile is weak. Did that answer your question? Okay, so there are more practice examples in the notes. In lab, I was planning on us doing a review of the practice final and the practice exam 3. So what we'll do is we'll take a quick 10-minute break and I'll see everyone in the laboratory meeting and we'll discuss the practice exams starting with the practice final. Does that make sense to everyone?
Yes, sir.
Yes.
When is the last day you're taking quiz corrections?
Thursday.
Thursday. Good. Thank you.
Mm-hmm. And it's just because I have to get all the grades in on time.
Okay, got it.
Mm-hmm.